All right, guys. So this week we're going to be going over reviewing some geometry concepts that we learned previously, and we're going to be applying them in some pretty hard problems. So some of these might be a little bit too hard, but our goal is just to go through and understand the process and see if we can relate these concepts in what we're going to be tackling today. All right. So start from reviewing, pretty simple, just similar triangles. We're going to be going some area of triangles and then area of rectangles and parallelograms. They're not squares. And you guys are still all familiar with this, right? We still remember all of this stuff pretty clearly. It should be not too hard. All right, so first review, some basic triangle similarity. So remember the three similarity theorems, right? We have AA, which is the angle-angle theorem. We have SAS, the side-angle-side. We have side-side-side, which is where all the sides are the same. So let's go over those real quick on these two triangles. All right, so for angle-angle is saying that if any two angles of these triangles, the matching angles are the same, then this triangle is congruent. So for example, we can have this angle here and this angle here be the same. So this angle down here, angle B, be equal to angle E. Right, and from this, you can tell that these two triangles are congruent, or not congruent, are similar. Because by having two of these angles be the same, we can know the third angle, right? Because we know that all three angles of a triangle will add up to 180 degrees. We can find this third one. When all the angles are the same, these triangles are similar. All right, another one here, we have side angle side. So that's saying if we have a side here, another side, and then an angle, and if on another triangle we have another two sides and angle here. So the angles must be equivalent and the sides must be in ratio. So AC divided by DF. So we're looking at this side here divided by this side. So the ratio of those two must be the same to AB divided by DE. All right, so if we know that, then again, we can deem these two triangles to be similar. And the last one we're going to go over real quick. Here's side, side, side. This one's pretty straightforward. So if AB divided by DE is equal to AC divided by DF, so the ratios are the same, which is also equal to BC divided by EF, then these triangles are similar. So the side angles must all have the same ratio. The side lengths, not side angles, side lengths must all have the same ratio. So does that all make sense? A little quick review. That's what we'll be using in the first problem. So are we all good on this? If you guys could thumbs up or just let me know in chat, or you guys can unmute. So I take that as a yes. All right. Let's move on. So the first puzzle, we have a 3, 4, 5 triangle here. We have a square inscribed inside this triangle. We're going to be looking for the area of the square. All right, so taking a look at this puzzle, do you guys have any ideas we can sort of branch off of? Again, don't expect to be able to figure this out right away. Well, this is a pretty hard problem. We're just going to try our best to go tackle this. You guys got any ideas for this? So the square is inscribed inside this triangle. You guys got anything? Any guesses? No? All right, that's fine. Don't worry about that. So let's go and try this out. So we're gonna go look at this on a Jamboard here, so I can draw on it. All right, so using the angle-angle theorem, we can find some similar triangles inside this bigger triangle. So can you guys try to go spot those? So we're using the angle-angle theorem that we just went over earlier. It's a little hint to get you guys started. Can you guys spot any of the similar triangles in here? Can unmute Lloyd, Jasper. You guys got anything? All right, well, that's okay. So let's go over and see what we can look at. So first of all, let's just start off with the big triangle, right? We have 3, 4, 5. And because 3, 4, 5 is a Pythagorean triple, we know that this is a right triangle, right? So we have one of the angles here equal to 90 degrees. And then also, let's take a look at what triangles we have formed in here, right? So first of all, we have, I'm gonna go over in red. We have the main triangle here. What other triangles can we spot, right? We can spot the one down here. We spot the one off here to the side, this triangle. You also spot this triangle up here. All right, so now that these triangles, we can all see them, how can we prove that they're similar? Again, using the angle-angle theorem. That's what we're going to be trying to figure out. So can you guys try to find some of the angles here that would make these triangles similar? Again, feel free to unmute or just let me know in the chat. And also, if I'm going too fast or too slow, or you guys need something to be explained again, just let me know. So any ideas? Okay, I guess not. It's okay. So let's take a look here at this triangle. Oh, sorry about that. 1 second, let me go back. So remember, we know one of the angles already given to us, right? We have the 90 degrees down here. And let's say we just mark out the other triangles of the main one, the 3, 4, 5. So we have an angle up here. We'll just mark that here with 1 line. And then we'll have another angle down here. We'll mark that with 2 lines. And also because we have this square inscribed in here, that allows us to find some right angles, right? With this square inscribed in here, we can find that there's a right angle right here. There's a right angle right here. And that's because this square has a right angle on the inside. So I'll get that. Oh, Jasper, you can't think of any ideas. All right, don't worry about that. We're gonna go over where you can find those angles. All right, so again, we have the 90-degree angles already figured out, right? So let's just find 2 of the angles here, right? Remember, for the angle-angle theorem, we only need 2 of them. So it's saying that if we have a right 90-degree angle here and the angle marked with 1 line, compare that to our big triangle here. Again, let's highlight that. Compare that to our big triangle, which also happens to have 90-degree angle, and this angle here that we've marked with 1 line through. So what does that tell us? Again, these angles need to be corresponding, right? So this triangle doesn't really look like the same, but we draw it out here. We flip it across 180 degrees and we draw it on the bottom. See, it's the same thing, right? We have the 90-degree angle, which we can draw out right here. You can have this angle on top, which is right here. And that matches up with our big triangle. So do you all see how we got there? Jasper, does that make a little bit more sense of how we got to the first triangle? Yeah, all right, cool. So using this same ideas, let's go look for more of the triangles, right? So we already know that this triangle up here is similar. So let's look at something a little bit easier. What about this triangle down here? Again, we already know one of the angles, this 90-degree angle right here. We just need to find one more that's matching. So do you have any ideas of that? So I'll give us a little hint here. Remember, because a square is all 90-degree angles, these sides are parallel. So we can draw out some parallel sides here. Oh, that's not really visible. We switch back to the red. We have some parallel lines up here and down here, as well as these sides. So how can that help us out? Again, we're looking for an angle here, either one of this one or this one, that can prove is equal to either this one or this one. So we can prove the similarity of that triangle. No ideas? All right, so okay. So remember, if we have this line parallel to this line, again, that makes this whole side of the triangle parallel. And what that allows us to do is to have this angle here equal to this angle in here. Does that make sense? Again, these two lines are parallel, so this line is parallel to this line. And that allows us these two angles to be the same. And then now, switch to laser pointer, now that we have this angle right here, as well as this angle right here, equal to this angle right here and this angle right here, we could prove that this triangle down here is similar to the bigger one. So now we have two similar triangles. Okay, so y'all see how we got there? All right, so now let's see if we can all figure out this last triangle here. How can you prove that this one is similar? Again, we're going to be looking for this triangle down here. How can we prove this triangle to be similar with our big 3, 4, 5 triangle? All right, Loy, Jasper, Zoom user, you guys got any ideas? Same concepts that we went over with these two over here. We're just looking for two angles, so we can use the angle-angle theorem to figure out the similarity. To know the right angle, yes, Jasper. So the right angle is one of them, right? We want to use this angle right here. So now that we used this angle, we already know one of them. We just need to find one more angle. One more angle in this triangle that we can relate back to our big one. So do we all see the angle here that is equivalent? C? Yeah, Jasper, you're right. So it's actually C right here. So this may not be too obvious at first, even though it's the same angle, but this may not be obvious since this triangle seems kind of different than the bigger one, right? But if we think about it, flipping this triangle upwards will give us this big triangle, right? So let me draw this out on the side. If we have this angle, this triangle here, we flip it, we actually get this big one here. So we have the right angle down here, as well as angle C, which Jasper pointed out. And we can see that this is the same as our big 3, 4, 5 triangle. So that proves that this is, again, similar to the big one. All right, so Jasper, I think, has got this. So Loy and Zoom user, you guys need a little bit more explanation, or are you guys good as well? Remember, if it's sort of confusing, you want us to go back a little bit, I can totally do that. All right, cool. So now that we know these three triangles are similar, how can we use that to our advantage? Let's take a look in the next one. So what do similar triangles tell us, right? Why are we looking for these in the first place? It's because they give us similar side ratios, right? So remember, let's go back to the slide here. Again, with these two triangles as our example, the sides have the same ratio. So side AB here, you do a little annotation. Side AB side AB divided by DE will be equal to side AC divided by DF. So the ratio of this side divided by this side is the same as this side divided by this side. So for example, if I said that side AB was of length, let's say 6, and side DE was length 3, and side AC was length 4, what can we sort of find out about side DF? Remember, going back to what we have here. All right, so if we write out this sort of equation here, you can see side AB is 6 divided by side DE, which is 3, will be equal to side AC, which is 4, and divided by side DF. Right, so these are in the same ratio, so now we can find side DF. Right, DF will be equal to just multiplying things out, right? We can just solve for it in this fraction. And something else that we can do is we see that side AB is just twice the length of side DE, right? And because these triangles are similar, we can infer that side AC is also twice the length of side DF. All right, so what do both of those things tell us about side DF? What is the side length of side DF here? You guys give me an answer. Give me a guess. You can type it in chat. Again, you can unmute. All right, well, so first of all, going by our side ratio example here, 6 divided by 3 is equal to what? 6 divided by 3 is equal to 2. And now we need to find 2 is equal to 4 divided by something, right? So 4 divided by what equals 2? 2. So you can find that DF is equal to 2. And then again, going by how this is half of this, again, same thing, right? 6 divided by 2 is equal to 3. So therefore, we're going to divide side AC by the same number. 4 divided by 2 will give us 2. All right, so we're going to be using this concept here of having the same ratio for the side lengths to solve our problem. So let's go back to the Jamboard. All right, so now using those, if we label the center side length of the square as side S, we can actually write out these two side lengths here in terms of S. And again, we did that by using the similar triangles. So you must remember that all of these triangles are similar to the 3, 4, 5 triangles. So that's going to be the ratios of the sides compared to each other. All right, so let's go over how we got to this one first, how we got to 4/3s. So if we redraw this triangle, this bottom triangle, let's highlight it in red for now, or outline it in red because we're working on it. If I was to redraw this, we would get something like this, right? We're just flipping it up. So we have this side here equal to S because that's the side length of the square. We want to see how we can get to 4/3 S up here. So this relates to 3, 4, 5, right? That's the side length ratio. So now if this S is 3, this bottom one, we would have to multiply by 4/3. Right? So does that make sense? We're going to find, again, this side here has shifted down here because we flipped the triangle over. Oh, not the angle. Let me make it a little bit more clear. It's shifted down here to the side because we flipped the triangle. And we're using the ratio here, 3, 4, 5, to find how, if this is S, we can write this as 4/3 S. Maybe a better way to explain this is, let me clear out this bottom here. If this was 3, right? Let's say S is 1 because it's only one variable. So if we were to do that, we would have this as 1. We would have to divide this side by 3, right? And because they're similar, we want to divide all the sides by the same number. So 3 divided by 3 give us 1. 5 divided by 3 will give us 5/3. And 4 divided by 3 will give us 4/3. If we replace this one here with S, or if we multiply, not replace, we're multiplying this by S, which is the length here, we would get 5/3 S and 4/3 S, which is how we get this right here. Okay, so that was kind of difficult. Do we all understand that? Jasper, Loy, Zoom user, if you guys could let me know. Explain again. All right, cool, no problem. So which part are you most confused about? You want me just, or you want me to just go over the whole explanation again? Confused? All right, no problem. So we'll just start over again. So Jasper, how are you doing about this? Is everything okay? Or you want to also go back? Well, we're going to go back anyway. So is there any specific part you guys are confused about? Jasper? Whole thing? All right, it's okay. No worries. Let's just go over this whole thing again. So first of all, we want to understand how we can redraw this triangle down here, right? Again, we're looking at this bottom one. So let's take this triangle and then flip it up, right? So the 90-degree angle is originally here. We're going to flip it up so that the 90-degree angle now rests here. So we're all good on that? Do you have to flip it up? No, you actually don't have to flip it up at all. We're just doing this so it's a little bit easier to see it in relation to this triangle up here, but flipping it is not necessary at all. It doesn't change any of the numbers. Again, we're just doing it so it's a little bit more easy to visualize how this triangle here relates with this one, and then our main 3, 4, 5 triangle. Okay, so again, these are all similar, right? The big triangle here is 3, 4, and 5. And this is similar to that, so we can also write it as 3, 4, and 5. Of course, with some variable, right? Because this is smaller, so it's getting shrunk. So do you understand that part? What I'm trying to say here is that the side lengths have the same ratio. So it's just a shrunk down version. And the hard part now is that one of these sides here is S. So does that make sense? How about I go back a little bit more? Okay, so we just got down here. We have this triangle drawn out. Again, it's in ratio with 3, 4, 5. So one of the side lengths here, again, because of the square, this is labeled as side S, right? And because this is a 3, 4, 5 triangle, we can say that this is, for example, 3S, 5S, and 4S. And this makes it similar to the big triangle, right? It's in some ratio. So the only thing we did to the side lengths to get from this triangle to this triangle is we multiplied it by S. And we multiplied all 3 sides by S. So do we understand that part? Everyone, are we good on that? This is probably one of the most important parts. You should understand, because if we understand this, we can write side lengths in terms of some variable or other number. Okay, so I assume we're good on that part. Alrighty, so we multiplied all these sides by S, right? And this is a variable. But now we want to write this as simply just a singular S, right? But now here it's 3S. So what can we do to all the sides? Remember, whatever we do to one side, we must do to all the sides because we want to keep this triangle similar. So to get from 3S to S, we simply divide by 3, right? So if we divide by 3, this here becomes S. This here, 5S divided by 3, will simply give us 5/3 S, or 5 divided by 3S. And then 4S will simply become 4/3 S. All right, okay, we good? So you guys can let me know if that made sense, or do you want me to go back, explain anything? Zoom user Jasper, we understand this a little bit better? All right, Zoom user says good. Jasper, how are you doing on this? Yeah? All right, cool. So just to reiterate, they're in the same ratio. We multiply everything by S to keep it the same, and then we divide everything by 3 just to get this from 3S to S. So now that leads us with what we want here, right? 4/3 S. Remember, even though this is on the bottom here, because we flipped it, it actually gets us to what we need here on top. All right, now that we understand this, let's just quickly go through the other bit. So we'll go through how we can find the other side lengths up top, which is 3/4 S. Okay. So this triangle up here is what we're going to be looking at. I'm going to give it a quick outline. Maybe better. Oops. Give it a better outline real quick. This one right here. This is what we're going to be looking at. So this is going to be pretty similar to how we found 4/3 S on the bottom, but this time the S is on a different side. All right, going back to our angles to see how we found this to be similar. This is the 90-degree angle. This angle down here will relate to angle C. And then again, this angle up here will relate to angle A. So again, we're going to we're going to redraw this triangle in a way that's a little bit easier to visualize. So we're going to get it and flip it. Right. So now we can get something again like this. The original triangle was sort of rotated a little bit and written this way, but we're just flipping it over. All right, now S has changed to the bottom, right? S has changed to the bottom. So now what do we do about this? We can fill in all the other sides, right? 3, 4, 5. Since the bottom is S, everything else has to be multiplied by S. And then we want to change this from 4S to just 1S. So we divide everything by 4. When we divide everything by 4, we get 3/4 S, we get 5/4 S, and then instead of getting 4/4S, we simply get S. Again, 90-degree angles here. So when we flip this back, we see that 3/4 S here will correspond to this side, which is how we get there. All right, so why did we do all of that, right? Why did we go through to find all this? Now that we know these 3 side lengths, what do we also know about side AC? Let's go back to the very beginning of the problem. Do you guys still remember what we know about side AC? So it's that side AC is equal to 5. Right, so what we did was we wrote out all of these lengths here. And then all of these added up. So 3/4 S, which is up top, added to S, added to 4/3 S, is equal to 5. Right? Because this is the original length of the triangle. 5 right here. Now that we know that, we can solve for S, right? Okay, we got to go back to think about what we're looking for in this problem, which is the area of this square. And to find that, we need to know what S squared is, so we need to know S. Now that we found this equation, we just simply solve for S, right? So let's put everything together on this side because this is where everything has S. So we change it, the bottom denominator, to something that's common. We have 4 and 3, so we're going to make it into 12. Let's give us 9/12S. Plus, I'll just write this out so it's a little bit easier. 12/12S plus 16/12S is equal to 5. Does everyone understand how we got there? Lloyd, Jasper, Zoom user, Jaden. We're all good on this part. All right, so now we can just finish up this, right, and solve for S. So we're going to add all these together. 9 plus 12 is going to give us 21 plus 16, 31 plus 37 over 12. S is equal to 5. So S equal to, be equal to, let's see, just 5 divided by this. And then now that we have that, we know what S is, right? It doesn't matter if this is sort of a big number. All we need to do is square S. So we can just put that in a calculator, square S, and let's see. Our answer will be around 2.63. We'll just say units because we didn't specify anything. So let's say it's around 2.63 units squared. All right, so there's our answer. That was a pretty hard problem. So hopefully you all understood that. Remember, the base of this problem, figuring it out, is just in similar triangles. We found the similar triangles in this bigger triangle that was formed by the square. And then we use those similar triangles to find similar side ratios to the one in the square. And then eventually you're able to solve for S and then find our answer. Okay, so we're all good on that. Let's move on to the next problem. Now we're going to review a little bit about area of triangles. So this one should be pretty easy, right? So again, area of a triangle is half the base times height. So the base is down here times the height. We're going to get half that will be equal to our area. And the important concept here that we'll be using in this next problem coming up is that it doesn't matter the shape of a triangle, right? So as you can see, triangle A and triangle B are shaped differently, but they still have the same area. And they have the same area because their bases are the same. Their bases are the same down here, and their heights are the same. They're both H here, and the height and the bases are both B. So again, even though they're shaped differently, they have the same area. All right, let's take a look at this next problem. So we have a big square. And in the square, we have a point here. And this point draws lines connecting to the midpoints of each of the sides of the square. So when I say it connects the midpoints, I mean that this side down here is equal to this side up here. This side is equal to this side, and so on. So it cuts the side length in half by the intersection point. So we know some of the areas they've already specified. So it's 20 centimeters squared, 32 centimeters squared, 16 centimeters squared, and we're looking for this question mark here. Alrighty, so let's start off by just seeing, does anyone have any guesses for how we can solve this? Any guesses, any ideas? Let's put it in chat. So remember, we're going to base our solution off this problem from the area of a triangle. So we're going to look for some ways we can build triangles in this square here, so you can find some relationships between the areas and figure out our answer. So does anyone see where we could potentially put some triangles? Just let me know in the chat. Jaden, Jasper, Loy, guys got anything? Zoom user? Any guesses for what we can do? No? All right, it's okay. So let's go back to the Jamboard here so we can take a look. So what we can do actually is draw some lines here to start and form some triangles. We're going to go from the midpoints all the way out to the edges. Let me get a better color that we can see a little bit more clearly. All right, so we can do that and form some triangles. Well, it's not a very straight line. There you go. So just forming all these triangles doesn't really help us, right? What we want is to find some sort of relationship between these triangles. So let's just take a look at these two down here. For example, let's take a look at this one and this one. So what can you observe about these triangles? Remember what we just went over in the quick triangle area review? Can you guys tell me some observations you guys can make about this? These bottom two triangles, how we can find some relationships between them. And again, this is an area problem, right? We're looking for the area of this sort of unknown section. So we want to be thinking of area. So any guesses at all? No? All right, so it's okay. Remember that these lines that I said earlier, they're hitting the midpoints of these sides, and that's denoted by these two bars here. That tells us that this little side here is equal to this side, so they have the same length. And also, since this point is where both triangles are hitting, this tells us that the height for both these triangles is the same. Right? And going back to what we just went over earlier, this means that their areas are the same. Do we all understand how we can get there? We're trying to say that the areas of these are the same. If you guys could just give me thumbs up or let me know in chat how we're doing, if you can understand that. No? All right. So I'm going to assume we're all good. But if you guys have any questions that pop up later, feel free to let me know. We'll come back. All right. So now that we figured out that these two triangles have the same area, we can start working on this problem a little bit more, right? So again, we drew these lines going to the corners. They have the same base and the same height. So that lets us, so now we can just go around and label some of these triangles. So we'll just go through, call these, we'll just go through and label them. And we're going to label these triangles so we can use what we know here about them being the same, so we can figure out the area of missing section. Okay, so these two are the same. They'll go through A and A, go through B and B, C and C, D and D. All right, so we do know, again, the problem told us the areas of these sections, right? So we know the section in green has an area of 20 centimeters squared, section in red has an area of 32, and the section in yellow has an area of 16. So now using that, we can just simply write out what we know. A plus B down here will give us 16. B plus C up here will give us 20. C plus D equals 32. And then A plus D will be equal to question mark. That's what we're going to be looking for. All right, so now how can you find this how can we find A plus D now? Now this is just down algebra, right? We've already figured out all of these side lengths and whatnot. So now we can just go find A and D. So how will we do that? Again, we're just going to be using algebra to figure out the rest of this problem. So could you guys let me know in chat any guesses you guys have on how to finish off this problem? Anyone? Any guesses? No guesses. All right, so let's look back at what we know, right? We know what A plus B is equal, B plus C, C plus D, and A plus D is equal to. So let's just know, so if we do A plus B plus C plus D, that'll be equal to A plus B plus C plus D, right? So in other words, we can rewrite this. So obviously, A plus B let's go back and look at what we have. We have a plus b here. We match that with c and d. Let me write this a little bit more clearly. C plus d. That'll be equal to what? The other bits, right? A, B, C, and D. So it'll be A plus D plus B plus C. All right, so do you all understand how we got there? Could you guys just let me know in chat? Yeah. So I know if we're on the same page here, if I need to go back to explain anything. No. Okay, so nothing. So again, I'll take that as a yes. So now we'll continue and finish off the problem, right? We know all of these areas. So A plus B is equal to 16. C and D will be equal to 32. A and D is what we're looking for, so I'll leave that as question mark. And then B and C is equal to 20. So now to find this, we can just subtract 20 from both sides to move this over. 16 plus 32 minus 20 will be equal to our answer. And that will be 28. So the area of the unknown bit is 28. All right, so do we all understand that? So turned what looked like a pretty challenging problem. We sort of shrunk it down a little bit. Just use what we knew about triangle areas to figure out some relationships between all of them. And then now we can get to our answer. All right, so wasn't that bad? Yeah, so these problems are pretty hard to look at, but once you sort of get through with the solution, not that hard. Pretty simple concept as long as you know the sort of trick behind the question. And so it looks like we won't have enough time to go look at this third problem here, which is a lot more difficult, but let's look at some takeaways for why we do these problems in the first place, right? So what we got from these is that in some geometry problems, we're looking for some weird areas, weird side lengths that we don't always know. We can look for some similar triangles, right? From the first problem, we can look for some similar triangles inside the original problem to help us figure it out. In this case, it was these three triangles. Be able to write some ratios to figure out the side length of the square. Right? Using the area is also very important, right? If we know that the area is going to be the same for some of these things, right? And especially in this case where we cut it up into different sections, that allowed us to find little sort of equations for what all these would add up to, right? In the end, we can just use algebra, cancel out what we don't need, and then get to our answer. So these will be important, in future geometry problems, especially in AMC. Using the similar triangles be really helpful for finding some of those harder problems. Okay, so that's it for this week. I guess we're going to be ending a little bit earlier. Again, if you guys have any questions about the problems, feel free to ask right now, and I'll stick around to go answer your questions. But other than that, I think that's it for today. So thank you all for coming. I know it's some pretty hard problems. Hopefully, you guys can take something away from these. All right, thank you guys. All right, Jaden, you got any questions about anything? Any of the problems? No? All right, cool.